Please, please, please. Shush. Thank you for your patience. Just airtime. Let's get going, gentlemen. Hopefully, in tomorrow's lesson, but just quickly look at where we're at. I might give you a quick little skills test on circular motion, which I can then mark and return it to you on Tuesday, so you can get some feedback for your test on Wednesday. Okay? So I'm just sort of warning you. Normally I'd surprise you with it, but at least this time, be prepared. You're going to be assessed on a circular motion question. We need to consider banked curves. So, a quick little recap. A wonderful equation can be derived when we equate the forces in the vertical and the forces in the horizontal. If it's a ball on a string, it's tension. If it's a plane, it's the lift force. Now, see, I can't yell at Robert because I'm holding a coffee. Robert! Was there voting at recess? Please hurry up and finish it and don't bring a sandwich into the class again. If it's a banked curve, now, again, please familiarise yourself with solving for this question. I've given the draft of the test to Dr. Rose, and she's worked it. One of the questions required doing exactly this. It was a 5-mark question solving for the junk down here. This lovely v squared equals rg tan theta, and then taking the square, there he is, v equals rg tan theta. So, not in the data sheet, you must derive. Please stop talking. Thank you. So let's get back to the banked curve example. Now, here's what I need you to appreciate. Here are these cars going around a banked curve. This is called a positive camber. What that enables is that the normal force, which is always perpendicular to the surface, now contains a horizontal component, and that produces the required centripetal force. That produces the required net force. I need you to understand that we've looked at inclines in year 11. In this case, Fn is not equal to mg cos theta. That is if you are stationary and sliding down an incline. These cars are not stationary. They are travelling around in a circular path. And I want you to imagine that as they're travelling, they want to travel in a straight line motion, and wouldn't you know it, the road actually kind of curves into them. So it actually produces a larger reaction force. We will find out it's actually in this example, so remember that is year 11, inclines. In this context, it's actually the opposite. It's n equals mg over cos theta. So all of these cars experiencing, let's not draw on that picture because I'm going to draw on it a little bit closer. All of these cars are actually experiencing a greater reaction force, and they're all going to be feeling a little bit heavier as they go around the track. Now, please recall, we have an equation for the ideal velocity, rg tan theta. Again, make sure that you derive. I'm going to write it here. This is called the ideal velocity where friction is not required. Okay? So in this case, the only forces acting are going to be the normal force and the weight force. So we're not considering any friction force that's going to assist here. Even though we know that cars have rubbery tyres and they will sometimes require friction, the question will prompt you calculate the velocity such that friction is not required. Or in fact, I remember when I was in high school, there was a banked curve made out of ice, such that there was no friction available. And you need to calculate the ideal velocity so that the cars could navigate around it. Okay, so again, the questions will prompt you. If friction is involved, it will be qualitative, or the values will be given. And I'll show you an example in a WACE exam where the values were given and you just had to sum the horizontals. Okay? So, but let's explain where friction might be required. I'm going to zoom in on this orange car. Now, I'm going to pick 3 cars in this scenario. Just wait a moment, hold off on drawing this until you decide what we're going to be doing. So here is our normal force. Okay? And then we're going to add the weight force. And then our net force acts inwards. Okay? And then obviously we have the angle theta. Alright? You will notice there that the normal force is the hypotenuse. It must be larger than the weight force. It must be larger than the weight force such that its vertical component is equal and opposite. And if it's acting inwards such that its horizontal component is what produces the net force. Okay? So again, I do not want to see students just going to, oh, I remember that from last year. Dr. Zander said that the normal force is mg cos theta. That is for a stationary incline where you are sliding down. We are now adding in sort of the third dimension where we're travelling around on a banked curve. In this case, friction is not required. However, what I would like us to do is just zoom in on that blue car in front of that yellow car. Here's what I would like you to consider. If this car slowed down, the normal force actually reduces a little bit. But the weight force is constant. Okay? Now, if there was no friction... Oh, hang on, wait. I'm going to have to draw this in a certain way so that it works. Hang on, give me a second. There we go. The weight force is constant. So if the car slowed down, you'll notice that now, sure, there's an inwards component. The car is still going to travel in a horizontal circle, but now there would be a downwards component. And the car, you would see, would start to sort of spiral down the track. If you were there watching that car, you would see the car slowing down and also sliding downwards. But of course, the car has tyres, friction. I'm going to quickly change colour to an orange. Friction will oppose... I'm going to go a little bit... There's my FF. Alright? Friction will oppose that downwards motion and act up the incline such that our net force still points in a horizontal manner. Okay? And you would notice the reduction in the net force agrees. If you're travelling slower, then your centripetal force is slower. All things constant, if V reduces, so too does centripetal force. Yeah? But we had to start with the idea that if I slow down, my normal force reduces. If my normal force reduces, then the net force acts downwards, but then friction comes in and saves the day and acts up the incline, opposing the motion that the car would like to slide down, and friction opposes up the incline and bumps us back up to maintain horizontal motion. Yes?
And the exact same process happens when the young thing is the
opposite. Let's pick. I've just picked the purple car for some room. Again, yep, spot on. Let's look at the opposite. If you go too fast, the normal force will be larger. All right, than the weight force. Whoops, hang on. I've got to draw the weight force ending a little bit up. Let's try again. There we go. No, hang on. Yeah, that'll do. Okay. And now, don't draw this, but if I was to draw in the net force, now we've got in and up, which again, the car would still travel in a circle, but now we would see it sliding up the bank. So if you were in a car neighbouring to it, it would be going faster than you and it would slide up and crash up into the wall at the top. Of course, that doesn't occur because now friction says, well, the car wants to slide up the incline. I'm going to oppose that by acting down the incline. There's my friction force acting, again, parallel. I should have drawn my little parallel lines to the incline. And now, the net force, you can still maintain horizontal motion if friction opposes. Remember, in the back of your mind, there will always be a limit to friction. That's mu times n. So the coefficient of the rubber on the road multiplied by this value, there's going to be a limit. So you can't just keep going faster and faster and faster. Eventually, you're going to have not enough friction, and then you can visualize this green arrow getting larger. That obviously has a limit, and then suddenly that now points upwards. If that points upwards, that car is going to be sliding up the road, up the bank. Okay? So, let's just go back to an example, just to put us in refresher mode. Let's suppose that we have an angle of 30 degrees. Okay? Now, oh, damn it. 25, sorry. I'm just going to use some values from previous. Let's suppose we have a mass of 1,000 kilograms of these NASCARs. And they might be travelling a radius, which isn't really shown, but a radius of curvature of 100 metres. Okay?
So is it an ellipse? How does an ellipse change the equation?
Well, okay, so hang on. At any point, it's the tangent at that point of their curve.
Okay.
And so, at any point, you can figure out the radius of curvature. If you're travelling in a non-uniform circle, that means your radius is constantly changing. An ellipse or an oval or any, just a normal road that might have a steep, a tightening turn or a opposite of tightening turn.
You take a tangent and
that
drop perpendicular line.
There's something called the radius of curvature. There's an equation that you can do in calculus that can calculate it. But that would be a changing radius. We simplify this to uniform circular motion. When I say the word uniform, you can go constant radius, constant speed, use these equations. If it's not uniform, you must be given the information at that point. So at this point, they're 25 degrees and they're travelling at 100 metres per second. Okay? Let's just take this one step further and figure out what the ideal speed is, and then violate that speed. So square root RG, oh shush, 100, 9.8, tan of 25. We get the ideal speed of 21.4 meters per second. Okay? That is the speed such that here mv squared on r, mg and theta. Okay, that's the speed that makes a perfectly beautiful right-angled triangle, which we can simplify into some lovely equations. If I go at any speed higher or lower than that, it's no longer a perfectly lovely right-angled triangle. It's this ugly quadrilateral. There's no nice equations for that. If we're going too slow, still, it's this ugly quadrilateral shape. We don't have any nice equations, but we do for the ideal velocity. Okay? Over here, let's just quickly figure out, and I'm going off script here, hopefully you have some room. Let's find out what the actual normal force is, Nx. So if we go back to our diagram, we worked out, we've got weight and we've got theta, so I'm just going to go over here. Oh wait, Nx. Nx is a centripetal force, isn't it? Yes, it is.
Oh, yeah, it is.
Yeah. In this scenario, it is. So there's our theta, there's our n. So Nx is the net force, which produces F centripetal, which is mv squared on r. So let's figure out 1,000 by v squared on, oh sorry, that should have been 1,000, on 100. Now I haven't solved this, so would somebody mind calculating that for me? Oh, go away. well, we can cancel a couple of these. It's going to be 10 by 21.4 squared. We'll get the centripetal force. Yes?
4.58 times 10 to the 3 newtons.
4.58 by 10 to the 3 newtons towards centre of curvature. Now, here's what you could be asked. Let's suppose that the car decides to increase his speed beyond the ideal velocity. Let's say that he guns it up to 25 metres per second. Now, all of a sudden, I need an mv squared on r to be a bit greater. Okay? Actually, no. I'm just realising that's not going to make any sense and I need to sit back and figure something out. So, here is a question that occurred Stage 3, so we're talking previous to 2016. It used to be called Stage 2, Year 11, Stage 3, Year 12. Now it's Unit 1 and Unit 2, Unit 3 and Unit 4. This was an example where you were given all of the values. So it's not an ideal velocity. It's not a beautiful right-angled triangle that brings out an elegant V equals square root RG tan theta. But calculate the radius of the track. We now would say, okay, I would have to add fx and I'm just going to quickly nx. So basically now we've got two x components. We've got the horizontal component of friction and the horizontal component of the normal force. Okay? And obviously everything's 20 degrees. Everything's 20 degrees. Everything's 20 degrees. So now, this was, again, as I said, you would be given the values, which you could then split apart. Without slipping means that my upwards force must be equal and opposite. Have a look. 11.5 to 10. I reckon if we did a bit of a cosine of 20 with that should give 10. So they've already figured out, they've already done the maths to make sure without slipping means in the vertical they're balanced. So all we need to do, if you were a student in this exam, is go that the sum of all forces in the x produces mv squared on r, and that's nx plus ffx. Now here we had to be careful. One's at one angle is to the vertical, the other's to the horizontal. So we've got to be careful. It's going to be 11.5 by 10 to the 3 sine. Thank you. Plus, and then obviously the f is 1300 cos 20. All right. So here was an example. I think it was like the 2015 or 2014 exam where you had to sum the x's. You were given the velocity. You were given the you weren't given the mass.
You divide the weight force by.
Right, so there's another mark. This is how many? 5 marks. There would be a mark for figuring out the mass. It's going to be 1,010 or 1,050 or whatever it is. Then there'd be a mark for figuring out that, putting it into the equation, solving for r. Okay? So that was just a nice little question that could have appeared in this year's exam had it not already been in this one. Okay? So, that's just a quick little higher and lower, up or down. That's basically just explaining my two examples about a reduced normal force if you're going slow and an increased normal force if you're going fast. That's just your explaining, okay? So that's banked curves. And I've realised that this next page could really have been back at horizontal circular motion. We could have done this page before vertical circular. But let's just quickly, again, this happens a lot, explain why people lean over when they enter the turn, etc., etc. So, here's our person running. What they have is their weight force acting down from their centre of mass, and the floor obviously exerts a normal force equal and opposite, so he's not accelerating into the floor and he's not accelerating into the air. Now,
Is this a bank curve?
no, this is just explaining why runners, it's not a bank curve. The question might say, why do runners lean in when they're running around a corner. Okay. Now, what I'm going to draw, these are the two forces acting on the runner. I'm going to draw a force acting on the floor, and I'm going to go back to my 0.5 mil thickness. So obviously you push down on the earth and the earth pushes up on you to stop you falling through it. But by leaning, what you also do is you push outwards on the earth. And the earth goes, yep, okay, if friction allows, I will act inwards. That's the reaction force provided by friction. Friction. So obviously we rely on friction being present in order for him to run around the corner. That is why athletic tracks are made of that rough rubber substance to have a high amount of friction. That is why if you try to sprint around the kitchen and there's a puddle of water, you're going to slip over and hurt yourself. Now if I said here's the thing. Obviously, we know that these two cancel out, and that's the net force which produces the centripetal motion, blah, blah, blah. There are two different ways to draw it. You could draw both. This will make more sense either is accepted, and there's been marking keys that say allow everything. So we could draw all of the forces in. Here's the normal. Then I'm going to draw friction. Then I'm going to draw the weight. And then our net force is the dashed red line that acts inwards. Okay? Or you could combine both. So
yeah, these are the forces acting on the runner.
On the runner. Yeah, we don't care about the earth. The earth is far too massive for us to notice any effects. The other option is to combine N and Y. It's N and FF, sorry. Combine N and FF into a reaction force. And so this is also acceptable. And I'll just add equals F, produces F centripetal. We'll just add that to our notes. Okay? You can draw in I'm just going to draw that a little bit less. Apologies if that stuffs you around. You can draw in the components if you want, but just draw them with a dashed line. Just be careful. Fn and Ff. And obviously the reaction force is the combination of the normal and the friction, which pushes inwards. Just be careful. That's the vector sum, top to tail. If you were asked for a free body diagram, which hopefully you've seen, it's basically just you exist as a box, and the arrows from the center of the box, all right, like so. So just be careful with that. Another reason why we lean over is you could be running and run around a corner staying perfectly upright. What would enable that is if your center of mass is directly above, your feet need to push out laterally, and you've got these poxy little adductor muscles going around your hip. They are very small, they are very weak. If you lean over, you got these big, huge lumps of muscles called your quads, your glutes, your hamstrings, and your calves, and they can generate a lot more force. All right? So essentially, when you're leaning over into a corner, you're utilizing a much stronger muscle group, and when that applies that force, the horizontal component of that force is then equal and opposite by friction. Right? So if you try and run around an athletics track at Ricky Wiley record speed and stay upright, you're going to strain all of those little muscles running around your hips and into your pelvis, your adductor, whatever they're called, muscles. Okay? So that's just another reason as to why we lean over. But for a physics answer, it is so that we can push outwards on the earth and then the reaction force of friction acts inwards on the person. And that is what provides, and we'll just, again, add here, provided by friction, we'll say produces, let me try again. Okay. Motorcyclist, same deal. We can draw everything again. Here's our weight force acting down, normal force acting up. The motorcycle pushes down on the earth, which would be, and also there's a little bit more going on with motorcycles because you've got a lump of spinning wheels, and you get something that's called gyroscopic precession. But again, we rely on friction. Or I should write it the other way around, that the sum of all forces is F centripetal, which is produced by friction, which then produces mv squared on R. Okay? Happy. We have 18 minutes left. Okay, here we go. There's a couple more questions. Wall of death. Oh, I didn't put that in my booklet from last year. That is a lion in a sidecar going around the wall of death. It's quite cool. Obviously. Oh, this was a wonderful question. I think I put this in a test a couple of years ago. And someone asked me in an email. Did I tell you about Mr. Murray's emails?
Oh, yeah.
Yes, okay. I don't think I told the other class. I'll have to remind them. The wall of death is a little bit of a trick. It relies on friction. And in fact, in these, there is a slight angle to the vertical. Even on this wall, it is not perfectly vertical. Obviously, moreover, the normal force provides, just trying to make sure, weight force has to be, friction has to provide the weight force down. There was a lovely question about, and I'm just going to scribble it off to the side. How much time? If you are on a perfectly vertical wall, which, imagine there's the wall here, and you are a square, then you require the normal force to be pushing towards the center of curvature, right? But you rely on, if those were the only two forces, you would be accelerating sort of that way, you'd be falling down. To prevent us from falling down, we need friction to act upwards. And there's a lovely equation that relates the force of friction is mu n. And we can say, well then, Ff on mu equals n, which is the sum of all forces in the x, which produces F centripetal, which is mv squared on R. So what I can now do is pick that, depending on my speed and my radius, and my coefficient, I need a certain friction. Let me just try and think. If mu is big, F is big. Yeah, that makes sense. And so we can simply combine the two. Oh wait, Ff on mu equals n. Oh, hang on, wait, I've stuffed up. I went off. This is what happens when I go off script. Obviously, Ff in the vertical, it's right, plus mg equals 0. Therefore, Ff equals negative mg. So I can throw him up there and go, well, now I've got negative mg on mu equals mv squared on r. Cancel. It depends, your velocity depends on a few things. The bigger the radius, the faster you can travel. The stickier the surface between the wall and the tyre. If that gets bigger, hang on, is that right? Mg on mu.
Yeah, because if you have something that's really sticky, then it's not going to.
But really sticky would make you travel faster.
Oh, no. Depends what you mean by sticky, as in like it holds.
Remember,
Well,
mu is a number
0 and
between
1.
0 and 1. It's just a coefficient.
Yeah, if it's not sticky, you have to go really fast to sample.
Thank you. Yes, if it's not sticky, we'd have to go much faster in order for it to work.
Proportional to
1 on V. If it was really sticky, you could go slower before you slip. Thank you. I got stuck in the wrong way. So if you have a nice rough surface with a rubber tyre, you've got a high mu, you can afford V to be a little bit less. Okay? I would direct you to, I made this question, I think, in the 2017 test one, which you are all going to rush off and start doing, because we're near to the end of our topic. Please download all of the past 5 years of motion test ones. Start working through them if you haven't already. Just remember, I'm going to give you a quick little validation test tomorrow. Well, hang on. Yes, I see you guys. Hang on. Yes, I do see. I see you guys tomorrow, but not Thursday. So I'll take it, I'll mark it, and I'll give you feedback. So it's important. I want you guys to get some feedback before the test. Okay? So we'll stop it there.